So if you use a population model, it definitely is mostly not a linear growth situation in most, I guess, situations. It's going to have like some steep incline. But eventually over time, like let's say we're talking about Comstock Park, right? Pretty small. And so it's growing. What eventually is going to happen? Is it going to continue to grow at that rate? No. Why not? What are some things that might impact that growth? Yeah, resources. What are some resources? Houses, right? Or land. Like there's just so much you can put in one area. So same thing for populations or anything that spreads exponentially, like a virus. A virus, a lot of times when people get sick, even in a school, okay, like there's some stuff going around. So it increases really quickly, but then it levels off. Why? Why would that not go to infinity? There's only a certain number of people in a school, okay? So the thing about Logistic that's different is it has that steep incline like exponential, but it also has something that we call the limit to growth. Okay, so there's two different equations you might see. One of them is going to be a C on top, over 1 plus A times B to the X. And understand that this is not, A is not the initial value in this case. Okay, this is not exponential. And B is not the growth rate either. Or you might see something like this. C over 1 plus A times E to the negative KX. Okay. In this situation, instead of B being in there, we have our K or our A right here, and then we have E, and then we have some constant going on. Okay, so those are the two ways that you're going to see it written today. And there are some properties about it that's going to help us sketch our graph. That's what we're really going to talk about. What's C called? That number on top, that's a horizontal asymptote. And if Whitney was just talking about like in the school situation, that would be the maximum sustainable population, or I call it a limit to the growth. And there's no calculating that you have to do to figure that out. It's literally the number on top. Okay, so let's take a look at an example. The number of students affected with the flu at Springfield High School can be modeled by the function P of t equals 1600 1 plus 99 e to the negative 0.4 t. Okay, now first of all, remember I said that this number here is my limit to growth. It is not the initial number. How do you find the initial number of things? What's time when I'm finding an initial value? 0. So one thing you want to really be careful of is that when we were doing exponential stuff, we had an A times B to the X, and we would say, oh, it's 99. It's not, because you're plugging it in this whole large thing. So we're actually going to plug in 0. So we have 1600 over 1 plus 99 times e to the, what's negative 0.4 times 0? 0. All right. So how does this work? Well, what is e to the 0? 1. So we have 1600 over 1 plus 99. What's 1 plus 99? 100. And 1600 over 100 is 16 students. All right. How do you think I'd find how many students were affected after 5 days? Plug in 5. Let's show on our calculators how to do this. Okay. So I'm going to show you, if you have one of the older graphing calculators, you're going to want to use a parentheses. So 1600 divided by, you're going to want to put this in a parentheses. 1 plus 99, and then you, again, like some of the older calculators, you're going to need a parentheses around your exponent. If you have one of the newer ones, it will put it in there for you. Negative 0.4 times 5. Okay. I did it too. There we go, I fixed it. You with me? We are. No, Brayden, we are. I just didn't. It should be an E there. My fault. Let's start over. 1600 divided by 1 plus 99e to the negative 0.4 times 5. That's better. All right, did you get 111.125? Okay, good. I just want to make sure we're cutting down on calculator errors. And because these are people, let's call this about 111 students. Yikes. All right. C, no work required. What is the maximum number of students infected? 1,600 students. And then for today, according to this model, when will the infected number of students be 800? You're literally going to graph. You're literally going to graph and find the intersection. Okay, so 500, 600, 700, 800. You can do this on Decimus or your graphing calculator. I provided a picture of graph for you. What would you say that is about? Yeah. When we learn about logarithms later on, we'll talk about how you can solve that algebraically. But for today, we're going to just solve things graphically. Okay. How do you graph these things? Well, let's just do A. So to graph, all I need the horizontal asymptotes. Those require no work. I require the y-intercept. That would be plugging in 0 and then a sketch of your picture. So first of all, one of the horizontal asymptotes is always going to be y equals 0, or the x-axis. The other horizontal asymptote is the limit to growth. So in letter A, where do I find that? Right on the top. So the very start of our graph, we're gonna make sure it stays below or in between y equals 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have y equals 9. Next, let's find f of 0. So we have 9 over 1 plus 2 times 0.6 to the 0. Well, what's 0.6 to the 0? One. 2 times 1 is? 2. 1 plus 2 is? 3. This is just 9 over 3, which is 3. All right, would you plot the point 0, 3? Okay, as far as shape of your graph, this is why I had you memorize when we did our basic function. You make it start exponential and then we make it level off. So it starts exponential and then it levels off and approaches that y = 9. So that's what your sketch of your graph should look like.